What if I told you that our solar system is surrounded by a 50,000-degree wall of fire? What if I told you that our solar system is surrounded by a 50,000-degree wall of fire? What if I told you that our solar system is surrounded by a 50,000-degree wall of fire? In 1977, NASA launched the Voyager spacecraft on a mission to explore the outer planets. Decades later, they journeyed beyond our planetary neighborhood and pierced the veil of interstellar space. What they found there was completely unexpected and reshaped everything we thought we knew about our place in the galaxy. It's a story of incredible engineering, surprising discoveries, and humanity's first true steps into the cosmic ocean. So let's explore this together.
The mission begins.
Think about this for a moment. How do you plan a mission into total unknown territory with technology from the 1970s? That's what makes the Voyager program so legendary. On August 20th and September 5th, 1977, NASA launched Voyager 2 and Voyager 1, respectively. Their primary goal was an ambitious grand tour of the outer planets Jupiter, Saturn, Uranus, and Neptune. This relied on a rare planetary alignment that only happens once every 175 years, allowing the spacecraft to use the gravity of each planet to slingshot to the next. The late great Dr. Edward Stone, who served as the Voyager project scientist for an incredible 50 years, was the guiding force behind the mission's scientific objectives. He and his team knew this was a once-in-a-lifetime opportunity to explore worlds we had only seen through telescopes. The probes were loaded with instruments like imaging cameras, magnetometers, and plasma detectors, all powered by a radioisotope thermoelectric generator designed to last for decades. This wasn't just about collecting data, it was about sending robotic emissaries into the void, pushing the boundaries of what was possible, and seeing what was out there for the very first time.
Journey outward.
Imagine being on a ship sailing into uncharted waters, leaving the familiar coastline behind for an endless ocean. That's essentially what the Voyager probes were doing. After their spectacular planetary flybys throughout the 1980s gave us our first intimate views of the gas giants and their dozens of moons, the Voyagers just kept going. Their trajectory was carrying them towards the edge of the sun's influence, a theoretical boundary that no one had ever directly observed. As they traveled farther, their instruments continuously measured the solar wind, that constant stream of charged particles flowing from our star at 1,000,000 miles per hour. As expected, the solar wind grew weaker, and its density thinned. This data was crucial for scientists like Dr. Alan Cummings, a cosmic ray physicist at Caltech who has been with the Voyager mission since its inception. He and his colleagues were watching for the moment the solar wind would finally succumb to the interstellar medium, the tenuous mix of gas, dust, and plasma that fills the space between stars. The journey was long, and the signals grew fainter, but the anticipation within the scientific community was immense. These probes were about to answer one of the most fundamental questions we have: where does our solar system truly end?
Crossing the heliopause.
What does it feel like to cross a cosmic boundary? While the Voyagers have no senses, their instruments told a story more dramatic than anyone expected. Scientists had long theorized about the heliopause, the point where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium. On August 25, 2012, Voyager 1 made history, becoming the first human-made object to cross this boundary and enter interstellar space at a distance of about 122 astronomical units. The final confirmation came from Dr. Don Gurnett and his team, whose plasma wave science instrument detected the vibrations of the surrounding interstellar plasma, which was far denser than anything encountered before. Then, on November 5, 2018, Voyager 2 followed, crossing at about 119 astronomical units. This small but crucial difference provided the first direct evidence that our heliosphere isn't a perfect sphere. It proved the bubble breathes, expanding and contracting with the sun's 11-year activity cycle. This monumental achievement, confirmed by two separate spacecraft at two different locations, transformed a theoretical concept into a measurable reality.
The wall of fire.
Now, here's where the story takes a truly wild turn. As the Voyager probes punched through the heliopause, their instruments detected something that, honestly, stunned the scientific community. They registered a massive and abrupt spike in plasma temperature, from just a few thousand degrees to a mind-boggling 30,000 to 50,000 Kelvin. That's up to 90,000 degrees Fahrenheit, hotter than the surface of the sun. This phenomenon was poetically dubbed the Wall of Fire. It's not fire in the way we know it, but a region where the solar wind, after its long journey, basically slams into the interstellar medium. This cosmic collision compresses and energizes the plasma particles, heating them to extreme temperatures. Dr. Stamatios Tom Krimigas, the principal investigator for the low-energy charged particle instrument on both spacecraft, saw the data come in firsthand. His instrument confirmed that the particles in this region were incredibly energized. This discovery showed that the edge of our solar system isn't a gentle fade into the void, it's actually a violent, superheated interface where two cosmic winds clash.
A superheated frontier.
So, a 50,000-degree wall of fire sounds pretty lethal, right? How did the Voyager spacecraft, built with 1970s technology, fly right through it without being instantly vaporized? Here's the critical detail: the plasma in this region, while incredibly hot, is also incredibly sparse. The density is less than 1 particle per cubic centimeter. Let me explain what that means. The air you're breathing has about 2.5 quintillion particles per cubic centimeter. Because the density at the heliopause is so unimaginably low, there's almost no heat transfer. The individual particles are moving at incredible speeds, which is what temperature measures, but there are so few of them that they couldn't transfer any significant heat to the spacecraft. Dr. John Richardson, a principal investigator at MIT's Kavli Institute who works on Voyager's plasma science experiment, has spent his career analyzing this data. The probes simply glided through this superheated frontier, their own temperatures dictated by their internal systems and the faint warmth of the distant sun. Their instruments gathered the first ever direct measurements, proving the edge of our solar system is not a quiet void, but an active, energetic boundary.
The dynamic shield.
The discovery of this superheated boundary also revealed something pretty profound about our place in the galaxy. The heliosphere, this giant magnetic bubble our sun creates, acts as a critical protective shield. It actually deflects about 70% of the high-energy, galactic, cosmic radiation that constantly bombards us from deep space. This radiation is harmful to life and, honestly, can fry spacecraft electronics. The intense heating at the heliopause is a direct consequence of this shielding process. NASA compares it to the bow wave formed by a ship cutting through water, a buildup of pressure and energy at the leading edge. The latest models, developed by scientists like Dr. Merav Ofer at Boston University, suggest the heliosphere isn't shaped like a classic comet with a long tail. Instead, her work, using Voyager data, indicates it might be shaped more like a croissant, with 2 large jets curling away from the direction of motion. This shape is likely formed by the interaction between the sun's magnetic field and the magnetic field of the local interstellar medium. Understanding this dynamic shield is crucial for protecting life on Earth and, for future deep space missions.
Magnetic mysteries.
Just when scientists thought they were starting to understand the heliopause, the Voyager sent back another puzzle. One of the biggest surprises came from the magnetic field measurements. Prevailing theories predicted that the sun's magnetic field, which is draped around the heliosphere, would be oriented in a very different direction than the magnetic field of the interstellar medium. Scientists expected to see a dramatic change in the field's direction as the probes crossed over. However, Dr. Leonard Berlanga, a key scientist at NASA's Goddard Space Flight Center who has been analyzing Voyager's magnetic field data for decades, found something completely different. Both Voyager 1 and Voyager 2 showed that the two magnetic fields were nearly parallel to each other. This unexpected alignment suggests a much smoother, more interconnected transition between our solar system's magnetic environment and the galactic magnetic field than anyone had predicted. It implies the boundary isn't a solid wall, but a more porous zone where magnetic fields from inside and outside can link up. This has sent theorists back to the drawing board to figure out how these two massive magnetic systems interact.
Cosmic ray barrier.
Another critical function of the heliosphere is to act as a barrier against cosmic rays, those really high-energy particles accelerated by distant supernovas. The data from the Voyager probes has given us an unprecedented real-time look at how this barrier works. As the spacecraft crossed the heliopause, their instruments detected a dramatic and immediate increase in the number of galactic cosmic rays, while the number of lower energy particles from our sun dropped to nearly zero. This was, honestly, the smoking gun that proved they had left the nest. Dr. Jamie Rankin, a research scientist at Princeton University who studies this phenomenon, uses this data to refine models of how the heliosphere acts like a semi-permeable membrane. It deflects most incoming cosmic rays, but, some still get through, and the number that penetrates is directly related to the sun's 11-year activity cycle. When the sun is active, the shield is stronger. When it's quiet, more radiation gets in. This knowledge is not just academic, it directly impacts our understanding of the radiation environment for astronauts on future missions to the Moon and Mars.
Interstellar space.
Voyager's journey beyond the heliopause marks humanity's first direct sampling of the interstellar medium. For the first time, we're not just observing the space between stars through telescopes, we are physically there, measuring it. The data the Voyagers continue to send back, though faint, is providing priceless information about the plasma density, magnetic field strength, and cosmic ray composition of our local galactic neighborhood. This is helping us characterize the small cosmic cloud, known as the local interstellar cloud, that our solar system is currently passing through. Dr. Ed Stone, in his later years as project scientist, emphasized that this was a new chapter of exploration. The data serves as a vital template for studying the astrospheres around other stars. This has, honestly, profound implications for the search for life, as the strength of a star's protective bubble could be a key factor in determining whether its planets are habitable. The Voyagers are our first scouts in this vast, uncharted territory.
Future missions.
As incredible as the Voyager mission has been, it is fundamentally a product of its time. The probes were built in the 1970s, and while their longevity is a miracle of engineering, their instruments are limited by today's standards. That's why NASA is already looking ahead. A proposed mission, tentatively called the Interstellar Probe, would be a dedicated successor designed to explore the heliosphere and the interstellar medium in far greater detail. Dr. Ralph McNutt of the Johns Hopkins Applied Physics Laboratory is one of the leading scientists behind this concept. The plan is to build a probe that could travel much faster than the Voyagers, perhaps reaching 1,000 astronomical units in just 50 years. Equipped with a suite of modern sensors, it could map the full three-dimensional structure of our heliosphere and analyze the interstellar medium with unprecedented accuracy. This mission could finally answer the lingering questions from Voyager, like the true shape of our cosmic bubble and the nature of the magnetic forces at its edge. It represents the next great leap in humanity's journey to the stars. From a grand tour of the outer planets to humanity's first steps into interstellar space, the Voyager mission has completely rewritten our understanding of the solar system and our place in the galaxy. The discovery of the 50,000-degree wall of fire at the edge of the heliosphere is a powerful reminder that even the supposed emptiness of space is alive with dynamic and violent processes. Even as their power fades, the Voyagers continue to send back precious data, their faint whispers from the void expanding our knowledge of the cosmos. Thank you for joining us on this incredible journey. Don't forget to like, subscribe, and hit the bell icon for more explorations into the cosmos. Until next time, stay curious. Thanks for watching Space Facts.